Thank you for that wonderful introduction. So our topic is SHAREM, Shellcode Analysis and Framework. My name is Dr. Bramwell Brizendine. I'm an assistant professor at the University of Alabama in Huntsville. I'm also the former director of the VERONA lab, which is the entity responsible for this research, creator of the JOP rocket for jump-oriented programming, and I'm also the PI on the research grant that allowed us to fund this wonderful research that we did. And I have a PhD in cyber operations. We have several different co-authors and contributors. They include Jake, Austin, Shelby, Sascha, and Tarek. Here today we also have Shelby and Sascha, who will be speaking. We'd also like to recognize other contributors, Evan Reed, Dylan Park, and Cade Brost. So let's start with a kind of a summary-style introduction to SHAREM. So it's a framework designed to be a total solution to anything and everything related to shellcode, and specifically Windows shellcode. Funded by an NSA research grant over a 2-year period, with $300,000, this allowed us to do a tremendous amount of work. Has numerous special features. It's able to emulate shellcode, including Windows APIs, and for the first time ever Windows syscalls. It has a custom disassembler with some unprecedented features that we will learn about. Additionally, it has the ability to do timeless debugging and brute force deobfuscation of encrypted shellcode. Now, that last point is one we won't have time to dive into, so I'll just briefly explain what it is. You can read about it in the paper if you are interested. So the brute force deobfuscation can enable us to deobfuscate the shellcode without emulation, and even without a decoder stub being present, and it also has support for distributed computing as well. Okay, so let's dive straight into the emulator, which is the heart and the soul of SHAREM. So it does utilize Unicorn Engine and provides support for both 32 as well as 64-bit shellcode, and again, Windows syscalls. Virtually all of those are supported. SHAREM is able to discover not only the parameters to these APIs, but also complete structures, which is also an unprecedented feature. SHAREM is also able to take this emulation data to merge it with a disassembler and to provide nearly flawless disassembly for the shellcode. So let's talk about the initial setup of SHAREM. It is a little bit unusual, a little bit different, but what we do is we go and harvest actual DLLs from syswow64 and system32, both for 32 and 64-bit shellcode. We harvest these, and then we inflate each of them a very precise amount according to the PE file format specifications. We kind of created a sort of formula allowing us to do that. The reason why is if we have a DLL on disk, it's not equivalent to the DLL once it's in memory, so it is absolutely necessary to inflate that DLL. So this is an initial setup step that does take about several minutes to do, but once it's done, then you don't need to repeat it again. We support 31 of the most common DLLs. We probably will add more later in the future. If you're a Linux user, then you'll need to place these DLLs in there directly. We'll provide a link to that in the future. And the reason for that is obviously we can't harvest Windows DLLs from Linux. So the PE file, a Python library, will actually go through, it'll analyze the DLL, and it will enumerate the runtime addresses, match them to the API, and then we can use that subsequently. With Windows shellcode, it is very complex, and it's a lot more complex than something like Linux. And so by necessity, we need to emulate and provide several different very special Windows structures, things like the process environment block, the PEB, the thread information block, the 3 doubly linked module lists, both for 32 as well as 64-bit, and map all of those out. If we don't do this, then the shellcode cannot be correctly emulated. And we do actually use real DLLs, as we mentioned. The reason why is because this allows us to be able to successfully emulate any and every shellcode. Certainly, we could simulate a lot of these values and that without having the actual DLLs, and that would probably work for a majority of shellcode samples. But unfortunately, not for all of them. So by having the actual DLLs in there, we can allow for the kind of sometimes bizarre, unpredictable behavior that some shellcode will do to function and to avoid it from failing. Of course, when the shellcode attempts to go to an API address, even though we have the actual DLLs in memory, we're not going to emulate that. Instead, we will simply intercept it, simulate an appropriate response, and then log it as well as all the parameters or even structures. So we actually created numerous different lookup dictionaries to provide support for about 12,000 Windows APIs. And so if we're able to, if the shellcode traverses the PE file format, goes through the exports directory, and then eventually finds an API that it wishes to call, when the shellcode goes to that runtime address, we'll be able to map that out to the appropriate API, and then we can use that API to then look up and see how many parameters do we want to extract from the stack. And then also information like parameter names, parameter types, return values, all of that good stuff. And so that enables us to provide support for thousands of APIs. Whenever possible, we endeavor to provide human-readable output. So hex 40 is something that's pretty well known as the FL protect value. It stands for pages execute read write. That's pretty predictable, but SHAREM also provides support for several hundred other values, so we can map out those hexadecimal values to the human-readable equivalents, just saving time so that the user doesn't have to look them up and try to figure out what the shellcode is trying to communicate to us. One of the ways in which we do that is through custom implementation. So we have several hundred custom implementations that allow us to do a lot more special activities with shellcodes, for instance, providing human-readable output. This also enables us to make sure that the shellcode APIs behave in an appropriate way. So, for instance, virtual alloc will actually create a region of memory, URL download to file A, will go and simulate downloading a file or even actually download the actual file. So all of that we're able to customize. And of course, something like structures, it's a very complex thing, and so that requires a custom implementation. However, if something is not necessarily very sophisticated, we don't have a need to do that, then we can make use of the lookup dictionaries. So here's an example of create remote thread, and you can see that it's highly modular. We have several different helper functions that we created to allow us to do a great deal with not taking up too much space. Towards the middle, you can see that we're able to actually firstly create a structure and then extract the appropriate values from the stack and from different locations in memory. It could be the heap, could be wherever, and then to be able to log those. So let's talk about Windows syscalls. So many of you probably know about Windows syscalls from egg hunters. Egg hunters have been around forever, 15, 20 years, widely used in exploitation, used in malware as well. And they very often will use a Windows syscall, but outside of that realm, until about 2018, they just were not widely used. As part of this research, one of our goals was to, again, be the total solution for everything Windows shellcode. And so that meant we needed to be able to emulate Windows syscalls. As it turned out, Windows syscalls in the form of shellcode is extremely rare outside of the context of egg hunters. So we actually did quite a bit of reverse engineering, quite a bit of research to make sure that we were able to have the appropriate and correct behavior. That also led to a separate presentation that we created for just this last DEF CON in Las Vegas, where we created a totally unrelated tool that will go and create syscall shellcode or help the user to do that. And we demoed an advanced syscall shellcode. So we do anticipate that while syscall shellcodes are not popular now, that may be something that may increase in frequency in the future. And when that does happen, SHAREM will be ready for it because we support virtually all user mode Windows syscalls. As part of that process, I want to track down the function prototypes for all user mode Windows syscalls. I got about 200 or so from undocumented NTDLL functions, some from MSDN, but more than half of them was just me searching for function prototypes whenever or wherever I could find them. But we do have them, and they are supported. And so what we will do is we will initialize fsc0 to point to a special location in memory. And so if the shellcode attempts to go to that location, we can then intercept it and then do our syscall magic. 64-bit is a little bit different, so we'll actually hook the syscall instruction. Here you can see an example of a syscall shellcode, int allocate virtual memory. It's also an int DLL function, but this is the syscall form, and you can tell because it's returning a value in EAX, the value of 15. And one thing about syscalls is its usage will vary based upon the Windows OS. For instance, Windows 10 has more than 13 different OS builds, and for each of those, the SSN values or the values in EAX can change. So if you are emulating syscalls, which again is not common, then you actually will want to specify the OS build, which probably will be the most recent build. Structures are a very important aspect of the Windows ecosystem, so we want to be able to capture these rather than just simply having a hexadecimal address to a structure. Why not go and get that entire structure? So we do provide that ability. So startup info-A is a widely used structure, and we do support that. And so if the function is set up for that, then it will just be automatically done and taken care of for you. So right here you can see that we have two structures that are captured from create process A, including the aforementioned startup info-A. And what about structures within structures? So this function is actually kind of curious, get time zone information. It actually has only one parameter, which is a pointer to a structure whose members also include two other nested structures, and SHAREM is able to display all three of them and also to visually convey that nested relationship for us. Unions, so unions can also be an important part of the Windows ecosystem. So a union is where two parameters will share the same memory, and of course we want to be able to parse that accurately, and so SHAREM does provide that ability for us. Whenever possible, SHAREM endeavors to provide success. So even if the shellcode is supposed to download a particular resource, that resource is not there, SHAREM will always simulate with every single API a successful result. So SOK is something that's pretty common, the hex value 00, which will be returned in the EAX register. And so some shellcode will actually go and check to see is 00 present in EAX. If it's not, it may prematurely terminate. So we'll do that, and also much more specific ways of trying to simulate success. And also output parameters. So the Windows will also utilize parameters, output parameters as well. So LDR low DLL will typically receive the address of the loaded DLL. And you can see that displayed there. We have the handle there, and we've actually converted the handle to shell 32. So instead of a hex value, we see the actual DLL that it's supposed to represent. Breaking out of loops, it's not a novel concept, but it's one that is incredibly important. So we do provide that ability. You can set it up however you like in the config file. Complete code coverage is probably one of the more revolutionary things about SHAREM. Inspired by AFL, which is a fuzzer that tries to explore every potential code path. SHAREM does something similar, so it wants to go down every single code path. So what it will do is it will record all code paths. It'll do that by creating a list of objects, and that will contain a good deal of information. For instance, the original location, the registers, the values of them, and also take a snapshot of the stack values. And in addition, it will dump the shellcode's memory. So when the shellcode terminates, if there are any unvisited areas of the code, SHAREM's going to restart, and it's going to revisit those lists until it has successfully visited all of them. And by doing this, we can discover more functionality. To the left, you see two APIs enumerated. And to the right, we are able to discover a third one, reg set key value A, which this is only accessible for one specific computer. And that's why we have get computer name A. So that's something that on any other machine would be completely inaccessible, but with complete code coverage, we're able to view that. Self-modifying code is a prevalent aspect of Windows shellcode, so shellcode decrypting itself in memory. And one very special thing that SHAREM can do is once the shellcode has decrypted itself, we will send the decrypted form to the disassembler, and we can view that. We achieve this by using SSD, but fuzzy hash, so we can just check to see how similar or dissimilar it is from how it started. And this is a shellcode that actually was or is encrypted, but we're viewing the decrypted form of it. So in a lot of ways, I view that as kind of a game changer for shellcode, because you can take something that is encoded and then view the decoded form of it in a disassembler. The same thing in IDA Pro. We have a decoder stub at the top and then a series of encrypted bytes. It's absolutely correct. It's just perhaps not as useful. And with that, we will then have Shelby.
The memory manager is responsible for the emulated memory being allocated. It also ensures that no collisions occur between multiple allocations. In addition to the memory manager, we also have a handle manager that is used to map handles to different objects. These objects can be a variety of types, such as registry keys, files, and other resources. If a handle object has a name field, we are then able to show that name instead of the handle ID. In this example, you see that two registry functions and their handles are instead being mapped to the registry paths that are being modified. The registry manager is responsible for the emulation of the registry tree. It handles all operations such as creation, modification. We are also able to read the values that are stored into the registry, and if the value has not been created yet, we can return a dummy value that is customizable via the config file. Throughout the emulation, SHAREM will record the additions, modifications, and deletions to the registry. Then after emulation is done, it'll go back and analyze for common MITRE techniques that make use of the registry, such as persistence and credentials. It also records and displays the hierarchy information for the registry. So in this example, we see a Windows syscall that makes use of the registry. We can see the path is displayed instead of the handle. We can also see an object attribute structure. And now Sascha.
So SHAREM has, whenever we do our API discovery and the data from it, we subject all of that to regular expressions to sort into categories. So here we can see categories with like command line and web artifacts. And then in this next example, we can see we extract all the paths, the files, which we maintain a pseudo file system for to keep track of any modifications, renaming, deletion, and so on. And then we also keep track of any web artifacts that do pop up. With web artifacts, we can actually download live files if the resource is still active and has not been terminated. So with an example, URL download a file, we would download the file, load into our memory, create an MD5 hash of it, and then use it where needed. This option is disabled by default, but it can be enabled through our config. And here we can see a example of a file being created with a successful download, along with the MD5 hash, and then the file correlations with our simulated file system, where this downloaded file has been renamed. If it is renamed or moved around in our simulated file system, it would show up right here. And we can see the web artifacts being popped up with a 200, which will be said successfully download from the website. And then back to Bramwell here.
All right, thank you, Sascha and Shelby. So SHAREM also provides functionality for a heap manager, which we actually implement very specific functionality for all aspects of the heap. Even though it's probably not necessary in most cases for shellcode, where we try whenever possible to be accurate, and so SHAREM does take care of that for us. We do support 64-bit shellcode, so we can emulate it and also disassemble it as well. It's not very common in Windows. It's typically 32-bit, but we do have that functionality. So let's dive into the disassembler. Now, what actually motivated this was my somewhat, I guess you could say, displeasure with leading disassemblers, IdaPro, Ghidra, Binary Ninja, and the way in which they would encounter a lot of, or disassemble a lot of Windows shellcode. So you could have data misinterpreted as instructions. Instructions would start at incorrect offsets. It was just very frustrating. So I decided to create my own solution. So I developed a disassembly analysis engine to provide that functionality. And at the heart of this, we need to distinguish for each and every byte, is it data or is it instructions? And specifically, where does it begin? Where does it end? If we're able to achieve that, then the resulting disassembly should be correct. So for each and every byte, SHAREM maintains complex metadata so that we can display the disassembly correctly. So our approach is exclusively with shellcode, and it's based very much on experimentation, a very empirical approach. So I had a lot of numerous Windows shellcode examples for which I possessed the source code. I would then look at them in a disassembler and try to figure out, why is this being misinterpreted? If I could identify the root cause causing it to be misidentified or misinterpreted, then I could correct it for all other instances. And I was able to be rather successful with that. So again, this is not designed to be 100% accurate, but it is significantly more accurate than leading disassemblers. There are several different disassembly analysis phases. For these, I will refer you to the paper. It's not really that interesting to talk about. But once we are able to achieve the more accurate disassembly, we can do things like put in API calls to APIs, which is something that, of course, no other disassembler is able to do. Not only do we have the API, we also have the parameters that are displayed, and it does support the syscalls as well. So instead of seeing something like call EAX, which is kind of mysterious, what's EAX or what's EBX? We'll actually see the label to the API. So incredibly useful. SHAREM does also have the ability to search and analyze the shellcode for a lot of very special things for which it collects many different data points, get PC instructions, your call pops, fast environments, push rets, which allows us to kind of discreetly modify control flow. Heaven's Gate, which I actually haven't seen in shellcode, but you potentially could do that. All of that is supported. PEB identification, we get many diverse data points, so you can display very unique aspects of the PEB, and that's all done automatically. API tables, so we can analyze the memory and determine something, for instance, could begin as a series of no bytes and then later be initialized to a runtime address, and we can have that updated, and so we can not only see what those specific bytes are supposed to be, but we also have them labeled. So let's compare IdaPro to SHAREM. So IdaPro, we're not able to identify the APIs, unfortunate. We're not able to see PEB information, also unfortunate. But over in SHAREM, we have all of that displayed for us in vivid color. SHAREM also has the ability to discover strings, has its own custom functions to do that. Some of them are slightly different. Down below, you see push stack strings are discovered, and you have an auto comment here for load library. One of the other very special aspects about SHAREM is it's able to utilize emulation data and merge that with the shellcode to achieve much higher quality, much more accurate results. Because if we emulate shellcode, then we can definitively know that a particular shellcode will start execution at this offset and then end at this offset. So we can take that data and then merge that into what would otherwise be produced. As far as data, we can analyze our memory reads and writes and then conclusively determine, hey, this is data. Other things like strings or D-word arrays for our API tables are pretty simple to identify. You might also ask, well, what about self-modifying code? Because every single byte of that is going to be read and modified. Well, we take that into consideration. So in that case, if we determine it's self-modifying, then we will only classify things as data if it's modified or accessed more than once. And so that solves that issue. And this one right here actually is encoded, but we see the decrypted form, and you can see clearly up on top, the instructions are clearly identified. We also see an API identified, and then down below, it's all data. Distinct types of data, and they are labeled correctly. If you were to view this in another disassembler, you would just see a series of bytes being misinterpreted as instructions, which they're not, so it'd be gibberish instructions. Now, one thing that SHAREM does, of course, is it tries to display the encoded shellcode as if it were decrypted. How do we do that? Well, we take a snapshot of the starting form and then the final form, and then after every CPU instruction is executed, we'll take an image of the specific bytes being executed, their starting and ending location, and then we will merge all of these together, the executed form, the final form, and the starting form. This way, if the shellcode were to re-encode itself, we would still be able to reveal its true inner form, which, by the way, that's not very common, but it's something that could be done. So again, here's another example of a decoded shellcode. We're able to see several different APIs identified for us. Timeless debugging. So timeless debugging can be extremely, immensely beneficial in analyzing a shellcode, or just really anything. And so what this will do is it'll log all CPU instructions executed by the shellcode throughout the life, the history of the shellcode from beginning to end. And we do this in a very lightweight fashion, so it's output just simply to a text file, and so you could, I find that visual code works very well, better than some other options for displaying it, so we can see the registers both before and after every CPU instruction. So we've actually used the timeless debugging on many different occasions to analyze shellcode and better understand its functionality or to troubleshoot different issues. SHAREM is also designed to be able to integrate with web services. So this was done from the ground up. So it can be deployed using a startup enabled config, and then it'll generate a JSON. That JSON can then be ingested by some web service, and then they can make use of that JSON however they want. So Black Hat Arsenal 2022, Aaron Baker presented subparse, and that parses many different types of files, and he actually used SHAREM. We worked with him, used SHAREM as the shellcode parser. He didn't talk about SHAREM or shellcode, it was about other things, but SHAREM was kind of a hidden feature there, and he was able to display that JSON output in his own fashion, which you can see down below there. That's not SHAREM output, that is subparse output utilizing SHAREM. So SHAREM reports on a rich set of data, probably a lot more things than you would anticipate could be possible with shellcode. It also analyzes PE files, which we don't have time to talk about, and it can also get traditional PE file features and some things that are somewhat related to shellcode as well. Gives a lot of data points on those. SHAREM provides several different outputs it'll print to the screen, and it'll provide text format output as well as JSON. And then additionally, for each shellcode, it'll generate a C file by default, so you could go and compile that in Visual Studio, and if you feel the need to actually debug it for real in WinDebug or whatever you prefer, then you have the ability to do so. SHAREM was first released today, so it's the first day that it's available right here for Virus Bulletin, so we hope you check it out, and we'd also like to thank our sponsor, the NSA. And with that, if we have time, we'll take questions.
Thank you very much. Thank you very much for your impressive work, and especially that. We have time for one quick question. Yeah, from Fredrik.
Okay, one really quick question. How big is the project in terms of how much effort has gone into it in man months or man years?
It was a tremendous amount, at least thousands of hours. I couldn't say how many thousands. We had several different people working on it for over a period of 2 years, but it's a lot of effort.
Okay, I'm going to sneak in a second question. It sounds like to me like you have almost everything you need for a full-blown PE file emulation, but missing some parts like multi-threaded issues and so on. Or is that something you have looked on? Have you looked on evolving this into a full emulator for applications?
No, we don't have plans to do that at this time. It's a great idea, but I think there would be a lot of additional work for that. But maybe we'll think about it. Thank you.
again.